Hello guys, welcome back to Mezone African Motives. Still on Power Machines N5, working on our revisions. We just want to check how questions given pertaining our steam or gas turbines and so forth, with the part of the velocity diagram in this case. How are you gonna have the velocity diagram at the end given a typical information? So as we know that we've got different types, so all you need is to make sure that you watch all the videos so that you'll be able to know each and every type, because I'm going to work different types of velocity diagrams that you're going to have depending with the information that you're given. All right, so I think that can actually help us. So this is question number 6 of November 2022 exam that we are given, and we're given the first part here, that the mean blade velocity of an impulse turbine. Take notes, we are dealing with what? An impulse turbine in this case. So this is what we are dealing with. That's an impulse turbine. So we just need also to understand the properties. That's why I was saying each and every part I'm going to talk about it. So when you are referring to an impulse turbine, we are simply having different, or we are not going to have the same length like what we have on a reaction turbine. An impulse turbine is the one that has got axial velocity. So this one, it has got the axial thrust, I mean. So this one we simply has with axial thrust, meaning to say we can actually obtain our force, which is the axial thrust in this case, which is the force, which we have the value for that, which is different when we are dealing with a reaction turbine, that one that is without axial thrust. But this one, it has. We shall see about that. It's only that in this question we do not have that question, but as we are revising, we shall talk about a question that can ask you to calculate that axial thrust. So it's just something that you just need to know on the different types of these. And here we're given 150 meters per second, which is the mean blade velocity. So that's our U is per our information, which is 150 meters per second. The amount of gas entering is 2.5 kg. So we're given the amount of gas that is entering, which is 2.5 kg. So this mass is taken per each second, per second. It's mass per second. All right. Then we are given that the gas leaves the turbine at an angle of 59 degrees. It leaves at that is the beta angle. That, remember, let me just save a sketch so that we just will understand later on as we are having the actual diagram. Remember, you are going to have the blade angle that is entering, and also have the exit at this point. Then we talk about these two angles that are that is our alpha and our beta. In this case, the alpha and the beta, talking about the steam entering or the gas entering the turbines, and beta, that is the exit part. So there we are given that the gas leaves the turbine at 59 degrees. We are given the value of this exit. It enters at this angle alpha, then it passes out at angle beta. So we are given the exit, which is our angle beta in this case. All right. So we have got the exit angle beta of 59 degrees in this case. All right. And the velocity of 200, meaning to say when it is leaving the turbine, it is leaving at this velocity, that is the exit velocity. So given at the velocity of 200 meters per second. This is the velocity at the what? At the exit that we are going to have when the gas is going out. It's going at angle beta and also affected by this velocity, which is the one that we are referring to as the actual, that is the exit actual velocity, or you can just say absolute exit velocity. I don't know the way that you're going to take it. So that is the one at the exit in this case, okay, which is 200 meters per second. I shall label my diagram later on properly. Then at the same time, we are given the blade inlet. I referred here the blade inlet and the exit. So the blade inlet, you can take this as theta, the exit, you can take this as phi. So we are given theta, which is the inlet, the blade inlet angle in this case, which is our theta, that is 32 degrees. And the coefficient of friction, we are given K, the coefficient of friction as a percentage. So you can just write this as a decimal, divide by 100, that's 0.807. We shall also see the application of this K. Where do we apply the coefficient of friction? And 6.1, in a landscape format, that is draw a velocity diagram by using a scale. We are given the scale to apply 1 centimeter is representing 25 meters per second. Label all angles and velocities in meters per second. So the velocities should be in meters per second, and you are supposed to label all the angles. All right, we are dealing with an impulse turbine in this case, as I explained from the sketch that we have, and this is the information that we are given about the gas. On our sketch, we are going to have every part here that we are given. So this is going to be our sketch. Remember, we're given a scale to use of 1 centimeter to represent 25 meters per second. All right, so that's 6.1. So on the sketch that we are going to have, we are going to present the information that we are given here, and also considering the diagram that it's an impulse turbine. So we are going to have the longer part on this side of velocity and the shorter part on this part, meaning to say this is what we're going to have on our sketch. So I'm just going to have the sketch. Take note here, this is a sketch. Then we're going to have the actual diagram later on. So let me just have my sketch here. All right, so this is where we're going to have our blade in this case, where we've got our mean blade velocity, which is our U in this case. All right. Then as we elaborated, the exit of our gas in this case and the input of our gas in this case. So we're just going to have something. We shall see the diagram later on, how it is going to be like. This is just a sketch like I illustrated here. So this is what is happening. We have got your initial, which is the value of the velocity, which is our blade velocity, that is our 150 meters per second. You see this thing of working with engineering science. Now I'm taking you as the initial velocity. No, that is our blade velocity. All right. If we are to consider, we say this theta, that is the inlet at the blade, that is the blade inlet. All right. You're supposed to know each and every part of your diagram. So this is the blade inlet, which is this one. So we've got our theta, which is equivalent to 32 degrees. And we also have in this case beta, which is the exit part of our gas in this. It is at an exit of 59 degrees. So this is your beta, the exit of 59 degrees, whereby we have got the inlet now to the turbine, which is our alpha in this case. Then we have got the exit at the blade. As we are referring to the blade, we are talking about the output of the blade in this case, which is phi. And we do not have these values. All right, so just present them as you know from your diagram. All right, so the other thing that you are given here, I think that's the only information that we have so far. All right, we have this also referring to the velocity of gas leaving the turbine. In this case, we are given the velocity of the gas leaving the turbine. So meaning to say, we also have this part here that is our absolute velocity at exit, in this case at exit, which is 200 meters per second. Let me just write it aside so that it can be clear, which is 200 meters per second here. So you're going to have our actual velocity at exit, which is 200 meters per second. That's the only information that we have. In this case, we do not have the input of the gas, which is in this case referring to the absolute input, that is the inlet velocity. In this case, we do not have the velocity of flow. In this case, we do not have the velocity of flow taken from this point up to this part. All these we do not have. So what are we going to do? We are just going to leave it as our sketch as it is. All right, so on your sketch, just leave everything as it is. Here we do not have the inlet our relative velocity we do not have, and also its exit here, it's in. Then we are talking about the exit in this case, which is the relative velocity at exit. We do not have all these values. Just indicate, but we do not have. And also the inlet angle, the outlet, the blade, we do not have all these. All right. And also we are given the constant, which is the coefficient of friction in this case. That's a constant. It's just a percentage divided by 100. So just a normal figure there. How are we going to apply this? It follows that the coefficient of friction is equivalent to the ratio of the two velocities, that is the relative velocity at exit, and also the relative velocity at the inlet, which is the inlet relative velocity in this case. These are the ones that we are going to work with: the relative velocity at the exit and the one at the inlet. So meaning to say, with this ratio, you can find whatever that you want, but we do not have any one in this case. We do not have this value. We also do not have this value. So for now, this part is not gonna work. All right, then let's go to the scale. A 1 centimeter is representing 25 meters per second, meaning to say we are going to change our U to what we can construct. We can't construct 25 meters per second. Nothing like that can be constructed. But we relate now to the centimeters to say it's a 1 centimeter for every 25 meters per second. And here we've got 150 meters per second. So our U, we are simply going to divide 150 divide by 25 to obtain the units or the length that corresponds in centimeters. So that is going to give us 6 centimeters in this case, all right? So that is going to be 6 centimeters. So meaning to say here, in place of 150, we are going to construct 6 centimeters, which is the same thing with the exit absolute velocity, which is 200 meters per second. We are simply going to do the same. It is 200 meters per second. We divide by 25. So that is going to give us 8 centimeters. So in place of this, we are going to use 8 centimeters instead on our construction part. So this is our sketch. Let us construct and see what we are going to have at the end. So this is a construction part, guys. As we can see, it's a construction. So a construction meaning to say we can play around the way that we want, as long we have the exact diagram that we need at the end. So what you're going to do is to construct, in this case, the first line where we are having our blade velocity in this case, all right, which is our U. So we are just going to construct here a line that is, for an example, we just assume we can have this along this line, okay? Then you measure properly with your ruler. Where are you going to have 6 centimeters? So in this case, according to me, 6 centimeters, as you can see, I'm just going to use this part. Here I'm having 0 to 6. So you measure properly 6 centimeters, all right? That is from this point, you're going to mark a point here, and also going to mark a point here. That is, we are having 6 centimeters at these 2 points, at this point, and at this point, we have 6 centimeters, all right? But since we are going to relate some other velocities later on, just try to have the other part as a broken line, because we are going to make some constructions later on. So the remaining of this part, we can just indicate with dotted lines. I shall talk about that later on. So you can just indicate this part as broken lines. In this case, just a broken line. We shall see the later part later on, like I'm explaining. All right. So we are having our 6 centimeters from this point to this point. These are the 2 points that we are going to consider. So we are saying from this point up to this point, it's 6 centimeters. That's our U in this case, which was 150 meters per second. But in the presentation, we are presenting the centimeters, but that is what we can construct. So we are presenting centimeters. So here, let me just write, but yeah, you are just suppose, because here they said write the velocities. And if you check here, we are given to write the velocities in this case, and the velocities in meters per second. So centimeters, just to show that this is exactly what I have in terms of centimeters, this is going to be 6 centimeters. The other information that we have on our sketch is the exit of the gas, which is 59 degrees. So how are you going to construct this? We are going to need from our instruments. You can just have your protractor in this case. Okay, let me just show you what I'm trying to say. In this case, we're going to have this presentation. So we simply need to measure an angle of 59 degrees at this point. At this point, we are going to measure 59 degrees going this direction. The angle in between should be 59 degrees. So how are we going to measure this? We are going to put our protractor this way. All right. It must be horizontally to the ground like this. You place this plus this thing, the line that is at 180, this line that you see straight line at 180, it must be at the starting point here where we are indicating our point here. And this line must cover your horizontal line. The line that we see of angles, this one, the horizontal line, it must cover your line horizontally. So we are going to place it this way at this point, covering our horizontal line, something like this. All right, so let me try to see if I can just enlarge so that you can see what I'm trying to say here. Let me, okay, like this. Okay, so this is what you're gonna do. You've placed this line covering your point and this line here, this one, covering the horizontal line. So you're going to measure, since we need 59 degrees, and this 59 degrees is from this point going this direction. So we are going to measure, or you're going to take your angles in this direction. That is how we are going to take our angle in that direction. So meaning to say 59 degrees, where are we going to have it? All right, 59 degrees. All right, sorry for that. We are going to have it somewhere. This is 10, 20. You measure these angles, not 180, 170. No, you're going to measure from 0, 10, 20, 30, 40, 50, and so on. So 59 is just below this part here, is just below what? 60 degrees. So we're going to mark a point where 59 is. So in this case, that is where our 59 degrees is going to be at this point here, this point. So you are going to join now from your initial point to this point with an angle of 59 degrees. So this is what you're going to have at the end. We have constructed an angle of 59 degrees here. So let me just try to see if this ruler can give me also 59 degrees. All right, 59. All right, let's see how it is going to be like at the end. So as you can see, my ruler can give me the exact angle, but you do not have, in fact, depending with the instruments that you have, there's that part where you are given the protractor and the ruler at the same time. So if you are using that instrument, you are going to simply measure your 59 degrees direct at that point. All right, so this line is presenting 59 degrees from that point. So we are going to join from this point along where the 59, this point of 59 degrees is, you must pass that point. So you're going to join passing this point. We do not know how long this line is going. So just draw your line exactly like this. Just indicate your line, something like that. So this is what you're going to have at the end. So be careful on the presentation part, right? So you are having your 59 degrees now. From which point? From this angle. So it's just an indication of an angle to say the angle that is in between here is 59 degrees, which is the exit of the gas, which is our beta in this case. So we have our beta, which is equal to 59 degrees. All right. We also know the length that is affecting along this line of 59 degrees. We also know the length there, that it must be 8 centimeters. We also know the length there. So without wasting much of our presentation, say we are going back there, we are simply going to measure 59, the 8 centimeters along this line. So this is what you're going to do. So now, because of these changes that I'm doing, it might affect my actual presentation, but this is what you're supposed to do. All right, you measure according to mine. This is where I'm going to have 8. You look, this 8 here is the one that you're considering, because you need 8 centimeters along this line. So you're going to do it this way along this line. This is 8 centimeters along this line. So you're going to mark a point at 0 here. So we are just going to mark a point at 0, meaning to say our 8 centimeters is ending here. That is where our 8 centimeters is ending along the angle of 59 degrees. This one, along this angle, we are going to have 8 centimeters representing what? Our exit absolute velocity, which is CI. So meaning to say CAE is going to be equivalent to 200 meters per second, which is in this case, we constructed 8 centimeters. So in this case, we constructed 8 centimeters. So that is up to this point, it's 8 centimeters. All right, we are done. Let's move on to the other point that we have. What else do we have? We have the inlet at the blade in this case, which is 32 degrees. We also have this angle. So we are going to measure this angle of what? Of 32 degrees in this case. We are going to measure our angle, right? So let us measure our angle, 32 degrees from this point. So this is what we need from this point. We are going to need 32 degrees. And if we are to check, our 32 degrees is supposed to be taken in a clockwise direction in this case, in a clockwise in this case. So 32 is going to be somewhere here if we are to take our measurement. So like I said, sometimes it might affect my presentation because of the reducing part of that I'm doing, but let's just hope you see what I'm trying to explain here. So the 32 degrees, this is from here, 0, 10, 20, 30. We are considering our angles this direction. So we are starting from 0. That's 0 here, 10, 20, 30. So 32 is going to be along the 30. 30 is along 150. So that means this is 31, this is 32. So 32 is going to be somewhere here. Where 32 is, you mark a point. You know that my 32 degrees is at this point. That is what you understand. My 32 degrees is at this point. Using now your ruler, you can combine now to the point, this point up to this point. In fact, you are supposed to continue from that point because you understand that is where you have what? Your 32 degrees in this case. All right, so we are going to join this point here and this point. So that is somewhere here like this. All right. So let me also try to change this way. Okay, something like this. It must pass this point, through this point, direct through that point. I think if I can place it that way, it can pass through the point like this. All right, so we are going to join. We do not know the distance also that we are going to relate in this case. We do not know our distance that we are going to relate. So what is going to happen? We are just going to draw this line. We do not know where it is going to be, somewhere here. So this is what you're going to have. We do not know exactly where it is going to end. We just know that is going to go somewhere there, just somewhere. We do not know exactly the point where it is going to reach. That one we do not know, but it will be something like that. I think this one is going to be enough. Maybe if I can just extend a little bit. You do not know what's going to happen. Maybe it can extend more than, but if it extends, then we are going to just join there. So this is along this line that we are having. Let me just put this one aside here. Along this line, the angle that is affecting, which is the inlet of the blade, it's 32 degrees in this case, which is the theta in this case, this angle here. That's our theta, 32 degrees. That's what we know so far. That's what our sketch can give us. So far, our sketch is limited there. That is what you have on your sketch. So the question is, you're asking yourself now, how am I going to have at the end the complete diagram? This is your sketch. The sketch is ended there. This is the information from the sketch. This information, it's ending there. It's done. So it's up to you and your construction techniques to complete this diagram. It's up to you and your construction techniques in order for you to complete the diagram. All right, let's start here. We actually know that at this point, there's nothing else that is going to happen. but to join between these 2 points, this point and this point, because we saw that from our sketch of the velocity that these 2 points are linked together. So we are simply going to join these points here. There's nothing to measure or nothing to do. So here we're just going to join, all right? So I'm just gonna join up to this point from this. Now we join direct because we are at the point exactly the one that we need, this point and this point. So these are the points that we are going to take from this point here up to this point like this. All right. So this one is a direct situation that we have. It's a direct situation that we can simply combine our points. This point connected to this point. We were not having the dimensions of this part. And remember, from this ratio, we couldn't even manage to find the value. I just listed the formula that consists of the coefficient of friction, that is the exit relative velocity to the input relative velocity. Now that we have this value, because from the construction that we have done, it means we can measure this distance in centimeters. So we are going to measure, that is our exit, in this case, our relative exit velocity. We measure the distance in this case. So now, because of this construction that I was doing, I was increasing the page, reducing the page also. So it's not going to give me exactly the value that we are supposed to obtain in this case. That's 12, but it's there, 12,2. But just because of the changes that we're doing, I increase, I decrease, and so forth. But the actual value that we are supposed to obtain in centimeters here is going to be 12,2 centimeters, which is equivalent to what in meters per second, because our values, they are supposed to be in meters per second as per given instruction. The velocities should be in meters per second. So we are going to convert now using which part? We are given that for each and every centimeter that we are going to have here, for each and every centimeter, it is equal to 25 meters per second. So that's we are going to use now that as a conversion to say, if I am given that 1 meter per second represents 25 meters, one centimeter represents 25 meters per second. What about 12,2 centimeters? So I'm simply going to multiply this time, 12,2 times the velocity in meters per second of 25. So if we are multiplying 12,2 multiplied to this value, we are going to obtain 305 in this case. So this is going to be equal to 305, which is now in meters per second. We are converting to say 1 centimeter is 25 meters per second. So if you are given 12,2, you simply multiply to 25 meters per second. So this here is equivalent to 305 meters per second. That's the equivalence in terms of the velocity. We just joined our points. Since we now have our exit relative velocity, that is the velocity at the exit, we now have this. That means we can also find the inlet velocity, which is the inlet relative, because there is a relationship that we are seeing from this formula here. What is the relationship? Let us consider our relationship that we said here. We said K is equal to, we have the value of K in this case. Our coefficient of friction is 0,807. 807. So we're going to have 0,807 is equal to the exit velocity, that is the relative exit in this case, which is the one that we obtained from drawing the diagram here. We obtained the value that is 305. So meaning to say we are going to have 305 over the inlet, which is the inlet relative velocity. That is the one that we are supposed to calculate because we need this inlet. So how are we going to calculate our inlet? Cross multiply, that's 0,807 is equal to, times the inlet is going to be equal to 305. So divide both sides by 0,87. That means our inlet relative velocity is going to be something like 377. So you're going to have something like 377, 94, something like that. But it's best for us to round off to the nearest whole number when dealing with this. So if you round to the nearest whole number, this is going to change to 8. So that will be 378 in meters per second. But just write the answer first, the one that you got. Then you can just write it approximates to 378 meters per second. So that's our velocity in this case at the inlet. So meaning to say we can also obtain what? The centimeters that corresponds here, because we are saying 1 centimeter represents 25 meters per second. So in terms of the centimeters, we are going to divide 378 divided to 25 meters per second. So if we divide, we are going to obtain 15.12. So this will be 15.12 centimeters. So we now have two things, the velocity and also the corresponding centimeters in this case, which is the length. So in this case here, we are just going to measure along this line because this is where our inlet, is supposed to be. So we are going to measure along this line. Already you have drawn this line here. So we are supposed to measure along this line. Maybe that was going to be somewhere along this line, 15 comma something. So you're supposed to measure properly, guys. Here it's because here I can't have it perfectly the way that you expect, but you are supposed to measure properly. Maybe your 15.1 to this one was going to be an approximation because you can have 15.1, but comma 2, it's gonna be difficult for us to have that value. So we just write in between the points. That's where maybe we are having the point what 15 comma the point 15.12 at this point. So meaning to say we are now having our inlet, which is CRI, which is equivalent to in terms of meters per second, we said is 378 meters per second. In terms of centimeters, we said it's 15.12 centimeters. So that's going to be 15.12 centimeters. All right. So that's it. That's what we have at this point. So meaning to say now it's possible for us to complete our diagram by joining this point up to this point. Now we can, because we know that this is the exact point that we need so that we have got the inlet of the gas in this case to the turbine. So this is what you're going to do. You just have to join the 2 points in this case. By joining these 2 points, we have completed our diagram. That's it. We have completed our diagram. Nothing here. So that is the whole idea here. Okay, so that's it. I'm going to join from this point up to this point like this. I have completed my diagram in this case. All right, so in this case, I'm saying I've completed my diagram, but after also completing your diagram, try to represent all the velocities, make sure they are there. So as we can check, we do not have this velocity, which is the inlet in this case, absolute inlet velocity of the gas in this case. So you're going to measure. So like I said, guys, you place your ruler from this point up to this point. So if you were to measure properly, this was going to give you 20.5 centimeters. Then you convert to meters per second, as we have our conversion that every 1 centimeter is 25 meters per second. So you're going to multiply the value that we got of 20.5 times 25. So we are going to multiply these two, which is going to give us 512.5 in meters per second. So in terms of velocity, our inlet is at 512 meters per second. So this is a 512.5, meters per second. Measure properly using your ruler. And also, if we are to check on our diagram, we do not have these 2 angles. That is the inlet in this case, the one of the gas, which is our alpha in this case. So you're going to measure your alpha again using what? Your protractor. So you're just going to place your protractor this way for measuring your angles. In this case, you're going to place it now down like this. This time it must be down like this so that we measure this properly. So it must be direct like, let me try to increase. Let me see if it's gonna give us exactly, but we are supposed to obtain something like 23 there. But this is how you're going to measure it. Here, it might not be accurate. Remember what I said before, but this is how you measure it, okay? You place this plus here, it must be at the center of point. Your angle is this one that is inside here, this one. So this angle is supposed to be taken in the clockwise direction like this. So this is how you're going to take your angle. So as you are going to place it here, you are going to measure this angle from the 0, that's 0, 10, 20, up to where this line emits your protractor here. So as you can see here, we are at 20. So it's going to be 21, 22, 23, yes, 23 something there. So this angle alpha is at 23 degrees, just after 20. So that's at what? At 23 degrees. So this angle here is at 23 degrees, which is the inlet of the gas. Also, we do not have the this one, the outlet part of the blade. Remember, this is the inlet for the blade. We also need the outlet of the blade in this case, which we consider as beta. Let me just as phi in this case. This is a phi like this, but you're supposed to write it here just because of space. I'm just going to write it here. So you measure again your phi, but this angle is this side. So you're going to take it from the anti-clockwise direction when you are measuring. So we are going to place our protractor again at this point. We measure, but this time in an anti-clockwise direction. So you need the angle up to where it reaches this line here. So where it is reaching the line, that is where we are going to take our point. Make sure it's directed that point directly at this point. So according to here, the angle that I'm going to have here, according to this point, is at 35. But the actual angle there was supposed to be at what? At 34 degrees, all right? So these are approximations definitely on your marking part. If the angle is at 34 degrees, you can write, maybe your angle is 35, write the answer that you're obtaining there. It's actually in an approximated value from that one that you're going to have, but we are supposed to have exactly something like 34 degrees. You never know, maybe ours is the one that is actually correct, the 35 degrees, but the idea there is the one that I'm simply explaining, all right? So this is the whole idea of the question. I think we have presented everything. Then we also need the velocities that we have after our diagram. In this case, we remember we've got the inlet flow velocity. In this case, at the inlet here, we're going to have flow velocity. At the exit, we also have the wheel velocity at the inlet and at the exit. Just indicate those. You never know what's going to, but you are supposed to indicate them. So let me explain it this way. All right, I'm just gonna do this way. Let's start with the inlet flow velocity, which is supposed to be extended. That's why I was saying this one, you're supposed to have it as a broken line because you never know what's gonna happen later on. So you're just gonna have a broken line like this. All right, we are supposed to have the flow velocity here, which is at the inlet. This is our flow velocity. But how are we going to construct it? On the actual sense, if you construct it here, it must give you an angle of 90 degrees at this point. So in order for you to construct this line, you don't just draw from this point to say, okay, I'm just going to place my ruler direct, unless you are having exactly an angle that corresponds here. So what you simply do is that since you do not know exactly your angle and also the distance here, because if you join, like I'm at this point, it's difficult for you to have a horizontal part here to say I'm horizontally at this point, because placing your ruler is not going to be accurate. That's why you see your values most of the times they are not accurate. For you to have accurate values, this is what you need. Understanding that if I'm to draw this line here from our construction, we know that the angle here is supposed to be 90. And angles in a triangle, they add up to 180. So I'm simply going to subtract these angles, this one, the 90, and this angle from 180 so that I have this angle here. By knowing this angle, I can construct that angle straight. So let me explain what I'm saying. Since we know that angles in a triangle, they add up to 180 degrees. already we know that the angle that we are going to have at the end here is going to be 90. So we're going to say 180 minus the 32 degrees and the 90 degrees like this, meaning to say the angle that we are going to have there is the one that we are going to use on our construction so that we obtain exactly a vertical line. We are obtaining exactly a vertical line. So the angle there was supposed to be something like 58 degrees. All right, this is what I'm trying to explain. So I'm going to take my protractor now. I measure this angle of 58 degrees. By measuring this angle, guys, it's a definite thing that you are going to have an accurate diagram. There is no way you can have a vertical line that is taken from these properties and it's not giving us exactly what we need. So we are going to measure. Okay, let me reduce and explain. Remember, when you measure the angle, you need to close this line. All right, so we're going to close our line. All right, horizontally. This line must close here at this point. All right. At this point, it must close. Let me increase it a little bit. So it must close this line here. It must be covered by the horizontal line where we want to measure 58. We want to measure 58 at this point, the angle that is going to make our triangle. So as we are moving here from 0, 10, 20, 30, 40, 50, 54 is just below 55. This is 55. So 54 is at this point here. This is where our 54 degrees is. From 0, 10, going this direction, going this way. So meaning to say, if I join, this is what's going to happen. If I join direct from this point, going to this point that I marked here, that line, guys, it's a vertical line. It's a straight vertical line that is exactly to the point that we need. All right, so this is what you're going to need here. Direct to this point, we are going to produce a vertical line by joining our angles in this case. All right, so just because of my movements, guys, please pardon me. All right, according to mine, it is going to be something somewhere here. But when you join, it's supposed to pass through that point that I indicated in the first place. But here, according to a proper measurement, this is what I'm supposed to have. But if you are to consider that angle, guys, this point here, this point was going to pass along this line that I just drew. But here you see, I zoom in, I zoom out, this and that, so it affects my angles at the end. But I just hope you understand this idea that I'm trying to explain, that you can have a vertical line direct, or you can draw direct, but be accurate on drawing your vertical line. So this is our inlet in this case, that is the inlet flow velocity. So we have got our inlet whereby you are going to measure, all right, using your ruler, you measure this distance. So if you were to measure this distance properly, according to my sketch, you are going to obtain 7.8 centimeters if you measure properly this distance. So maybe yours, it can be 7.7 or 7.9. Use that value that you obtained, all right? That is it. But we need the velocity. So we are going back again to the conversion where we are told each centimeter represents 25 meters per second. So we are going to multiply by 25 meters here. Meters per second, we are going to obtain 195 meters per second. So we have got inlet. We move on to the exit. We do the same thing as we understand the concept that this is going to be taken to the right angle, triangle, and so forth to complete this. So we're going to subtract 180 minus 59 and the 90 degrees that we need, that we know that is going to have here, which is going to be the angle that you're going to use now. So that is the whole idea. With the angle that you're going to have of 38 degrees, you are going to construct straight, you measure like I did previously, but here let me just join. So you're going to measure straight that angle of 38 degrees from this point going up. But if you can draw this line straight up, please do so, but make sure that it's accurately a vertical line. So this is what you're going to have at the end. And I just need these points. So let me just extend. I'm going to need these points later on, these points here. All right. So this is what we have at the end. Meaning to say, we have the exit, in this case, flow velocity, which is you measure. So our exit flow velocity was going to be something like 6.9 centimeters. In terms of centimeters, it was going to be 6.9 centimeters. But we need the velocity. So we go back to the conversion. 1 centimeter is representing 25 meters per second. So multiply by 25. This was going to be 172.5 meters per second. We have the velocity there at the exit. So then we can talk about the wheel velocities. In this case, the wheel velocities, these are the ones down here. From this point direct here at the exit, at this point, we can measure straight. Let me put it this way. I want to measure straight to the point that is corresponding here to this point here. So just along that line. So that is the wheel velocity in this case, which is this one, the whole of this length from this end, from the input to the end. So this whole distance that we have in between here, let us just indicate this whole part here is our wheel velocity, this one. So we have the whole part, which is our wheel velocity. So that's we're gonna measure, which is going to be 23 centimeters. If you measure properly, that was going to be 23 centimeters, all right? So that means in terms of centimeters, we've got 23 centimeters. You measure properly with your ruler, guys, properly, all right? Then convert this to meters per second. Remember, 1 centimeter is 25 meters. So we're going to multiply by 25. So that is going to be 575 meters per second. If you multiply that by 25, go back to the conversion. Also on our wheel velocities here, if we join straight from this part of the turbine where we've got where we talk about the inlet and the exit. If we are to join straight, we can have two velocities that are being constructed, which is the exit of the wheel and the input of the wheel, which is the inlet in this case. If we are to take it straight from the blade part, this one here, we are just going to have a broken line straight, all right, here, straight like this. So as it reaches our velocity here, which is our wheel velocity, as it reaches this, we have a distance between these 2 points. All right, we have got a distance. Let me just remove this part so that I do not confuse you guys. All right, so we have this one here, this velocity straight in between these points. All right, we can just indicate anywhere of your choice. From this point up to this point that we took here, there is a velocity that we are considering here, which is at the exit. Then the inlet is now this one that is remaining. So you can just join from this point up to this point here. So the remaining part here indicates or represents the inlet, which is this point, this whole length. So that means here the inlet wheel velocity, if we measure from this point up to this point in terms of centimeters, that was going to be 19 centimeters. Then multiply by 25. Remember our conversion, 1 centimeter is 25 meters per second. So you're going to multiply by 25. That was going to give us 475. So we now have 475 meters per second. And at the exit, the wheel velocity at the exit, if you measure from this point up to this point using your ruler, that was going to be 4 centimeters in this case. So that's 4 centimeters times 25, which is going to be 100 meters per second in terms of your velocity. So that's with this information, we've completed our diagram. We have completed our diagram. Every information that is needed on this diagram, we have it. Every information is there. So make sure that you take the information that you are given as it is, the way that you are obtaining from your diagram. Take the way that you are obtaining from your diagram. If it is 18 centimeters or 18 comma, write the values that you are obtaining. They are supposed to be approximately in within these values that I'm indicating here. Your values should be approximately in within. All right, so let us check the other part of the question now. What are we given? From this diagram, that is from our velocity diagram in this,
Yes.
determine 6.21, the nozzle angle, 1 mark for that. So the nozzle angle is the one that we consider our alpha in this case. This is our nozzle angle in this case, which is the gas in, that is the inlet of the gas, that is the nozzle angle, or we can present as a discharge, which is our alpha in this case. So our alpha in this case, it was 23 degrees, all right? So that was 23 degrees, so 6.21, our alpha was equal to 23 degrees, right? Then let's check the other one. What are we given in this case? We are given the relative inlet velocity, the relative inlet velocity in meters per second. Remember, our relative inlet is CRI, the relative inlet velocity in meters per second. Already, we calculated this. We are just taking from our diagram. We already calculated this. Our relative inlet, it's 378. So that's 6.22. Our relative inlet velocity is 378 meters per second. All right, so you're just taking from the diagram. Then what is it that we have also? Also, we are given the 6.3 by using the diagram. Also calculate the power required in kilowatts. 3 marks for that, the power required. So the power is given by the formula. All right, so this is the formula that you're gonna use for power, that's 6.2. Power is given as the mass in kg per second. In this case, this mass is supposed to be taken in kg per second, times the blade velocity in this case, times the wheel velocity. So if you already on your diagram, we've measured the wheel velocity, we have it 575, the mass, we have it. So everything we have here. So you're gonna substitute our mass. We are just gonna take our mass. We have from our information, remember, from our information here, I listed the mass somewhere here, 2,3 kgs. So you're gonna have 2,3 kgs in this case. That's our mass. All right, so that will be 2,3 times the blade velocity in this case, which is given as 150. That is, we have this one, 150 meters per second. So that's 150 times the wheel velocity. We have this, which is 575. So that's the whole idea that you need in order for you to obtain the power. So this was going to give us something like 198 375, which is in watts. But take note, we are given to calculate this power in kilowatts. So that means divide by 1,000, we are going to obtain 198.375, which is in kilowatts in this case. So that is how we can have our information presented if we have the diagram direct as it is, instead of you working out to say the inlet plus the exit, then you add, you already have calculated from the diagram, you can measure that one. So you simply use the equivalent wheel velocity to the mass and the blade velocity in order for you to have the power. So as you can see, that's how your questions are given. So like I said, make sure that you watch all the videos so that you'll be able to understand each and every diagram, how it's given. We have got different types of velocity diagrams, whereby we are representing to an impulse turbine, the one that is with axial thrust. We also talk about the reaction turbine. We shall see those ones in our next classes, whereby we can have a reaction turbine in this case, which is the one that he has got without axial thrust. So this one is without axial thrust in this case, which is the force. All right. And we can talk of whereby the turbine discharges axially. All right, whereby we have got a discharge axially in this case. That's a discharge axially like this. So we shall see different questions or different diagrams that you're supposed to consider. So make sure that you play around as we are revising so that you won't miss out. But for now, that's it till we meet again.